Thank you for the invitation to have us here. And today we'd like to share a book plan or book in progress. And with my former PhD student, my current postdoc, Rebecca Barter, which we believe is a new framework for practicing and teaching statistics. So in case you're wondering what it means by Veridical, actually means truthful. So really we want to do a reliable data science analysis. So let's define what's veridical data science. Veridical data science we define as the practice of extracting reliable and reproducible information from data. And we really want to train a generation of practitioners of data science that are able to effectively evaluate and communicate empirical evidence in the context of human decisions and domain knowledge. So actually the book plan really started when I was trying to bring the interdisciplinary experience my group had to classroom. So for us, Veridical really is being implemented by people. So it's really a whole ecosystem of data science, not just the algorithm, the data, but the context, the domain problem we try to solve, the critical and liberal art thinking skills we bring in, and of course, this algorithm inference. And also we use theory to support the practice. And also we have to explain interpretable conclusions. And we take the view of data science with three components: computer science, math and stats, and domain knowledge. And the whole team should definitely cover all three components. So the class I started teaching about 11 years ago. It's a Statistics 215A. It's a PhD course on applied stats and machine learning. Actually, Becca was a wonderful TA a couple of years ago when I started working on the book. And I want to share this comment from a student from system engineering. So the class, 2/3 actually come from outside statistics. So this person wrote that Stat 215A is the only course that manages to properly emphasize the issues of interpretability, ethics, and pedagogy in the application of statistical methods without sacrificing any of the technical rigor one would expect of a graduate level statistics course. So this kind of summarized from the user point of view what we try to do. And the course is really built on very broad interdisciplinary research experience I had from Bell Lab time, signal processing, audio compression, and work on network tomography, remote sensing for 10 years for my group, cloud detection, aerosol retrieval. And also later, about the last 15 years, we've been working on neuroscience, very much embedding my student in the labs. That's one approach we believe in. It's really work next to a scientist. And also more recently, genomics, Rodolfa developed biology, and even more recently, precision medicine. We've been working biohub scientists with UCSF and Stanford to understand the genetic components of hard problems. So all of that, the goal I set for the class was, can we try to bring the reality, like practicing statistician data scientist or machine learner as close as possible to the classroom. So later developed into this book plan with Rebecca joining me to put it into a book form. So the teaching approach I took was really hierarchical organization of concepts. I felt like more the traditional approaches have been like a lot of more like details, methods. And for beginners, it's kind of difficult to get into everything before you can see the big picture. So for me, I kind of was taught in a traditional way from different methods, and took me many years through teaching to really see actually there's, I believe, a simpler way, a more effective way of teaching this practice or these skills through basic principles, right? And also work in a diverse team to have people help each other to learn. And bring in common sense intuition. I do use math, math, relevant math is very important. And build on intuitions and common sense and interpret the math symbols in the context. And also the course was really run with real data and real problems and with open-ended project. It's not like question and answer. It was really, if you want to solve the problem, And we allow people, of course, encourage people to take a different approach. And actually some of the students, master's students in my class would use the class project for interview projects. And we really embrace the whole data science life cycle, not just the modeling the data after it's cleaned. It's really, we're building a system when we build a pipeline on analysis, the problem formulation, and we make so many human judgment calls in every step along the way until we reach conclusion. And we want to really make sure that our conclusions are robust or stable to this different, I will call perturbation analysis, like linguistability. You have multidisciplinary team working on the same problem. Does matrix mean the same thing for cancer biologists and a data scientist? Actually, in cancer biology, they also use the word matrix and mean something different. And all of this, we want to, for people to see the whole pipeline, not just isolated steps. And we really, for the quality of the conclusion, we have to worry about every step. In particular, basic principle, we talked about hierarchical organization. I want people to embrace the PCS framework. Me and my group have been developing for the last 10 years. It's really try to bridge Leo Breiman's two cultures, machine learning and statistics, and expand on both. Predictability really was in statistics, but really was put at the center of attention by machine learning. And computability, you have to deal with computer from beginning, data collection and data storage. And stability is expansion on the uncertainty concept from traditional statistics like sample to sample. It's a perturbation, different samples. But for every step, problem formulation, there are different ways to clean the data. There are different ways looking at the data, visualizing. There are different ways to model, say, particular genetic component is important. For particular cancer, you can do lasso, you can maybe also do random forest. And every data perturbation, model perturbation, kind of unify the different sensitivity and robust consideration under the framework of stability, and then push it forward. We have PCS inference. We have perturbation intervals, which is kind of extension on uncertainty or confidence intervals, taking into account the many, many perturbations, often driven by human judgment calls in the process. So let's expand a bit on the predictability. In some sense, prediction is in every problem. When we do data analysis, it's never that we kind of freeze time and care about today. It's always something tomorrow. You want to treat a patient. It's a future patient, most likely. And even when you want to build new knowledge, it's the knowledge will be transmitted to future students. So there's always a future component, even in the problem formulation. You want to know what you're doing now for what future task is relevant. In popular scientific philosophy, predictability is really a falsification method, right? It's really, we can use it for reality check. If things don't really generate good predictions, you're probably not capturing the structure in the model or in the data by the model. So you should doubt whether things work. Of course, the threshold of what's good prediction now depends on the noise levels. So that should be context dependent. And predictability is really to connect reality through collected data. And you need to think about future data and the algorithms, right? So it's really, reality and algorithms really have no connection unless you have minimum reality checks through predictability and relative to the collected data and future data. And after you ensure predictability, then you can also attempt at interpreting the model like variable importance. Stability is really a common sense principle that you talk to anybody, like you said, well, I made a different judgment call, another statistician analyzed data, you should get similar conclusions. Otherwise, really worrisome. It's an artifact of this particular perturbation to the process, right? If you just add white noise to some ImageNet data, would you get the same result? There are many different forms, and you need to argue, use documentation which is appropriate. And many human judgment calls are really underreported, under-recognized, that you might have different results. If you have two different graduate students clean the data, would you reach the same conclusion? And also problem formulation as well. So we need to worry about the stability or robust consideration, which is really unifying many things in the literature under this stability banner that we need to perturb and see what happens. Of course, this is exponential expansion of possibilities, but I think at least you should do some checking, at least do two different pipelines minimum to make sure that you reach the same conclusion. So now I turn to Rebecca for the second part of the talk.
Okay, yeah, so I'm going to talk about the specific topics that we are going to cover in the book, which is very related to the topics that Ben covered in her course. So there are a lot of topics that we do cover that are kind of traditionally covered in stats and machine learning courses, including dimensionality reduction, exploratory data analysis, clustering and prediction, and machine learning. But we also cover these traditional topics from a very non-traditional perspective. So instead of kind of just introducing a model and giving a formula for it, we really try to kind of guide the reader through the process of discovering the method. So for example, if you're thinking about k-means, you know, we think about, okay, what's the problem that we want to solve? We want to be able to group similar observations together. How can we do that? Well, you know, we have to kind of think about what does distance mean? We have to come up with a way of, okay, let's say we want 3 groups. Maybe we can randomly place 3 points and just kind of group the observations that are near each of those points together and just kind of come up with a lot of suggestions and follow that kind of logic train through and find that we get to the methods that people typically use. So I think it really helps with people understanding these traditional methods rather than just accepting them. But in addition to kind of treating traditional topics in non-traditional ways, we also really introduce a lot of not traditionally taught topics, including all of these topics listed here that have asterisks next to them. So I'm going to go through these in a little bit more detail. So one of the early things that we talk about in our book is how to formulate a problem and collect appropriate data. So this is obviously incredibly relevant to every single data science problem, every single data science project where, you know, it's not always obvious how to formulate the problem appropriately such that you can answer it with either data that you have or data that you are going to collect or that your collaborators are going to collect. There's a lot of things that you need to kind of think about in order to be able to do that adequately, and it's really not commonly taught in courses. Another thing that we focus on pretty early on and throughout the book as well is that data is messy. So traditionally people will teach data problems by giving students a really clean and easy to use data set. So we don't do that. What we do is we give the students really messy data sets and we teach, you know, how to clean. And, you know, it's not an easy thing to teach because there's no single formula that you can just apply to every data set. And so I think that's why it's not commonly taught, because it's not easy to do. But what we do is guide through many examples of cleaning and things that you can check and things that you can do to kind of arrive at a clean data set, emphasizing that there's no single definition of a clean data set. There's many different versions of a clean data set, and a lot of it comes down to judgment calls about what you think the data set should be when it's clean. We also focus on communication. So again, Ben mentioned this, talking about when you're working on a data science team, typically you're not just working with technical people. You're also working with domain experts and non-technical people who you need to be able to speak with a common language, and you need to, it's really important to learn to you know, explain things in a way that non-technical people can understand, but also you, like as a data scientist, you need to learn to take the information from domain experts and use that in your own work. It's really, really important when you're coming to arriving at, you know, valid and reliable results that are going to be used in this domain in the end. Another really important thing is documentation. So scientists have been really good at this. You know, they have like lab notebooks where they document everything they do, all their experiments. in data science, this is also a really, really important thing to do that isn't done nearly as much as it should be. You know, every time you make a decision or a judgment call, if you document what you did, it's really easy to then go back and check that those decisions that you made didn't affect your results. But if you didn't ever write them down, if you don't have kind of a log notebook, a lab notebook, you're never going to be able to do that. Obviously, you know, you can use an R Markdown file or Google Docs or whatever you like. Another thing is it's really important to document your code, especially if other people are going to come and look at it, or future you is going to come and look at it. And providing README files for project folders, repositories, because often things get really messy and it's hard to kind of just look at something and know how everything's structured. So documentation in a lot of different ways is really important throughout the whole data science lifecycle. Another thing we talk about is different ways of validating results. So traditionally, people will check model accuracy if we're talking about prediction. It's how well do we predict? And maybe they expand it to looking at, you know, true positive and false positive, or sensitivity, specificity. But we also want to start having people check the stability of their results and think about the interpretability of their results. Another thing that is really, really important that I think industry does a lot better job than academia is ensuring reproducibility, replicability, and code review. So the best thing that you can do is have someone else replicate your results. And I don't just mean, you know, hit a button and see that everything runs. I mean, you know, they take the data and code up the whole pipeline themselves and see if they get the same results. The second best thing is you do that yourself. So you do it, you get your results, you're like, great, I'm done. Then you go back to the beginning without looking at what you did and you try and do it again and you see if you get the same thing. I think most of the time you won't, which is a problem. And the third best thing, which is sometimes people do this, is you or someone else will just reread the code after it's written. So these are things I think very much need to be brought into academic data science. I think is more a part of in industry data science. But you know, how can we really be putting our results out there if we haven't really checked that they're correct? And this is something that's really important in science in general. And it's just so easy to make a typo and not notice. So this is something that we do talk about throughout the book as well. Finally, we also want to bring in this idea that data science is iterative and cyclical. So it's not that you go through, you know, you start, formulate the problem, collect some data, clean it, explore it, model it, check it. You know, you're frequently going to be going backwards as well. So you might, you know, formulate a problem, collect the data, realize you need to change your problem based on the data that you have, go back to formulating the problem, then proceed to cleaning it, realize, oh, you actually need some different data, have to go back to collect the data, then you end up exploring it and you realize you have to clean things a bit differently. And, you know, it's very much iterative. It's non-linear, and I think it's really important to emphasize that, you know, you can always return back to earlier stages of projects. So at the end of the day, I think what Ben and I are both trying to say is veridical data science is just data science done right. It's data science done responsibly, and that's why we called our book Veridical Data Science, the practice of responsible data analysis and decision making. So we're about to hopefully sign a contract with MIT Press within the next few days. So our book is hopefully going to be available online early next year, and the physical copy of the book, depending on how long it takes to print, will be available late next year. So yeah, thank you so much. If you want to get in touch with either of us, here are our emails, and you can reach me on Twitter as well at Barter. Thank you for listening.
Just one more comment is that the free online version will be interactive, so the codes will be embedded and you can run on some test data and do coding at the same time. So that's why I think the free online version is very important, because you cannot do that in the book form.
Yeah, exactly. There'll be a GitHub repository with all the projects and examples with code and data.
Yeah, thank you.
Yeah, thanks everyone.
It is wonderful to be speaking here today. Even though it's remote, I'm hoping that we can have some good Q&A and possibly follow up afterwards. So my name is Rayid Ghani, and this is joint work with my colleague at Carnegie Mellon, Kid Rodolfa, and my previous colleagues at the University of Chicago, Adolfo de Unanue and Matke. And this is work that reflects some of our thinking over the last several years that we developed thinking about training students to be effective and responsible data scientists. At this point, we all probably agree that data science is very much an applied discipline, and training our students to be both effective and responsible practitioners means doing it in a way that's very much applied. Yet that's not how we've designed our curriculum and our coursework in pretty much most programs that attempt to teach it. So how does this type of training happen today? A lot of people have just learned ad hoc through online content, videos. Some people go to boot camps, and they'll take a 4, 6, 8, 12-week boot camp. Many people go through degree master's programs. There are probably a few million of them. Every university probably has 4 right now. Yet most of the real training, and you talk to employers and you talk to students, is really happening on the job. And a student gets a job, that's when they figure out what they need to learn. And a lot of that training, if you're lucky, really happens on the job, and you figure out what you should have learned earlier. And so what's this gap between our programs that exist in a lot of universities and the skills that are needed? Well, it turns out that, not surprisingly, a lot of students entering industry or the public sector with a master's degree in data science may have a very strong foundation in understanding the technical details of a wide variety of methods. They might know how a neural network works or a random forest works, and they might understand a lot of the theory and can code those things, but they have very little experience in choosing the right method for the right problem, for the given problem, applying that method to messy real world data with real world constraints to evaluate and develop this work, and then explaining the results of their work to different decision makers and stakeholders. We've repeatedly heard about sort of deficiencies in experience in sort of communicating the work, as well as, a lot of these programs are not grounded in a strong foundation of ethics, which means students coming out don't have an idea of issues around data collection and data use, neither ethical nor legal. And the other issue comes up is that a lot of the coursework involves working on very well-defined problems, whereas real-world problems don't come well-defined. You need to understand how to scope and define a problem. You need to understand how to communicate around it, not just at the end, but also in the beginning to convince somebody to do this. And so what we've been doing is running different programs over the last few years, teaching both students and professionals to do practical data science. And those programs sort of range from graduate programs at University of Chicago, a joint program between computer science and public policy, Carnegie Mellon, same joint machine learning and public policy programs, as well as summer fellowship programs, one called Data Science for Social Good that brings in typically graduate students from computer science and social sciences and statistics and engineering and work on projects with governments and nonprofits, as well as programs for government agencies, such as the one Coleridge Initiative. And what we've kind of learned from that is how do we bring students who have this, who want to learn practical data science, how do we provide them training? And so our proposal is really a data science residency program, a residency master's program that's structured around applied project work that's supported by lectures and workshops. And it's really flipping what today's programs are like, where it's primarily today's standard program has a lot of coursework, and then the project is really a capstone type project where you come in and then you do a project, and really don't believe it's an effective way to train people in an inherently applied discipline. So a lot of our motivation for this proposal is coming from medicine, where medicine being an applied discipline has developed residency programs that's augmented with coursework and lectures, but really focused on the practice of a discipline. And when we look at this structuring around a project, we still need some coursework and prep work but that work is really coming in as it's needed rather than long classroom-based lectures. And when we step back and look at sort of what types of skills we need to give our students for them to have an impact, today we might take a computer science centric program and add some statistics to it and call it data science, or you might take a statistics focus and add some computer science, or you might take a social science focused program and add some statistics and programming. And it turns out that when we're trying to solve real problems, we need a lot of these skills. We need all of these skills. We need to understand how to formulate a problem, because no real problem comes well formulated. We need to understand how to validate what we've just done through designing an experiment. And in computer science, an experiment is something you run in your computer overnight. And we don't train our students to actually design an experiment and conduct it. Same for communication. We might do communication at the end of a project, but what about at the beginning when you have to convince somebody that this project is worth doing? And then ethical and legal issues in which this project is being conducted, how to have those discussions with both the people this project will affect, but also the people who are going to be involved in this project. And so what we've done is kind of a proposal sort of breaking this down into these core domains that we need to teach our students. We teach them how to do formal formulation, how to deal with data prep, how to do analysis and modeling. That's where we'll bring in computer science and social sciences and statistics. How do we evaluate results, not just again on historical data, but looking forward in field trials and randomized trials or A/B testing, and how do we embed all of that in rigorous professional ethics curriculum that's part of everything we do, as opposed to at the end where you might do a review. And then how do we teach students to communicate about the work again throughout the problem? And so if we situate this into a life cycle of a project, here's what a project typically looks like. Like most of us have done real projects. You typically start with identifying a problem. In many cases that might be given to you, but in a lot of cases, you might have to identify what is this problem worth solving. And then you might go and scope the problem to understand what the goals of this project are, and what actions it might inform, or what data it might use, which then leads you to acquire data. And this process is not necessarily linear. You often go back and iterate through as you might get data, you might figure out the data is not what you expected it to be. So you go back and rescope the problem. And once you've acquired either an existing data that you already have and sitting in some database data warehouse, or you might have to go out and collect additional data. You then do data exploration, and then that leads you to actually formulate the analytical problem. Right? Most of the projects we look at don't come formulated. It's not, you have these features and you have these labels and you have a matrix that you build a model on. You get messy problems that you then form into an analytical question that you then define your labels and rows and matrices and features and training tests and test sets. And then leads to you to do the analysis and the modeling. And then you might trial that in the field and to do validation. And if that's successful, you want to implement that and inform actions so that it has the impact that you want it to have. And so given this messy, iterative, cyclical project lifecycle, what we want to do is create this cross-section of the skills we want to teach connected to this project lifecycle. And some of these skills are heavier in certain parts of the project. So the problem definition is going to be heavier in the beginning of a project, but you might need to come back to it as you go and get data, do analysis. You might find out that you have to redefine the problem. Data prep is typically going to be in the beginning, but you might find that you have to your data wasn't good enough, or your analysis wasn't accurate enough, so you might go back to get better data. And so different components are heavier in different places. The two things that are heavy throughout, one is ethics, because ethics is not going to be a one-off course or a lecture. It's going to be embedded into every single phase of the project you're in. You're going to think about what are the ethical implications of different design choices that I'm making in this phase of the project. And how do I mitigate some of the risk based on the choices that I'm making today? Same for communication. We're going to have to teach students how to communicate differently at different phases of a project. It's not just about doing a presentation. It might be how to communicate to the problem owners in the beginning, to the people who might take action based on your problem, and to the community that's going to be affected, the people who you're going to be changing outcomes for. Involves communicating differently. The skills you require are different for different types of those communications. So what we're really proposing here is a different way of doing a data science graduate program, which is really anchored in a project that starts in the beginning, the first day you show up, where you start defining the problem and talking to the project partner, and goes on for the entirety of your master's program. And this coursework and classes and lectures and workshops are embedded throughout to support the type of work you're doing throughout the project. So we're hopeful that this type of a program, really inspired from the medical residency program and centered around an applied project as the focal point of the degree, it ensures that students hopefully develop the skills they need to be successful data science practitioners. And while the coursework and the theoretical basis of the methods is an important part of a student's experience and should remain so, it should expand to several disciplines: computer science, statistics, social sciences, and it should serve to supplement and enhance their applied work rather than act as the primary element of the program. Before I stop, I want to plug in the spirit of sort of working on real problems. I'm going to put a plug in for if you're a student, or if you're a senior data scientist, you want to work on real problems. We've launched this website called Solve for Good that connects volunteers who are interested in helping nonprofits and governments with projects that are coming in from governments and nonprofits. So it's a great tool for both learning how to do this, but also making an impact. So happy to talk later about this, but I wanted to put in a plug here. And then there's some resources for people who are interested in more content around sort of practical data science methods and methodologies and tools. So thank you very much. And we'll now switch to the live feed of the Q&A and the discussion. And if you're watching this video in advance, please tune into the time of this talk, and I'm happy to take any questions. Thank you.
Thank you very much, Rayid. I'd like to take this opportunity now, before segueing into our broader discussion, to pose a question to Rebecca and Ben, as well as to Rayid. So if the three of you could all come on to camera when you get the chance, I'd be curious to hear your answers to this question, which is that, you've each described a great vision for what data science curriculum might look like. And the question is, how much power do you feel you have to implement that vision, and what are your greatest obstacles?
For us, I think I have this class right now. It's only like 30 to 40 students. Actually, the bottleneck is actually number of GSIs, but I have been hesitating to increase because the classroom discussions with smaller class, like 40, it's a right size. If you go to 80, that'll be a very different experience. That's something I think I want to develop a lighter version of this class for Berkeley data science for the whole campus. But that, I think, will have to be creative. Maybe this online, I'm doing online, will give us good lessons to scale it up. So I think it's really the human interaction has been the bottleneck. I mean, Becca, do you want to add things?
Yeah, I was just going to say that, since we are writing a book about this, hopefully, I think a big issue is also the lack of resources. There aren't a lot of resources out there for kind of teaching, not necessarily veridical data science, but teaching responsible data science with practical skills. And so I think just helping get some more resources out there will help to have more people teach these kinds of courses.
Yeah, that's a great point. Actually, the reason we're writing the book actually is because the scaling up. I mean, I could teach the class 40 students or 30 a year, but actually the book idea came about because we try to have access to more people. And we're going to have a free online version and probably do some blogs. And we're also going to do workshops and tutorials and get other people to teach from the class. So Texas A&M, Jian Huang, who's the chair there, already offered to do a summer for us. So we go there and train other people teaching from the class, how we can try to scale up.
Yeah, I mean, I think for, similar, I mean, it feels like we gave very, very, very similar talks and very similar ideas. I could have probably swapped the titles and nobody would have known. I think the cost is, you know, universities, the way that the current structure is set up is classes, a faculty member teaches a class in a semester and all these hours, and not just come in when needed and not give continuous feedback. You know, most PhD students see their advisor an hour a week, and that's a luxury. And I think cost is the biggest thing. Is universities are set up to sort of do this. You know, we wouldn't expect it efficiently, but to some extent efficiently. And I think a much more practical, hands-on program requires much more frequent feedback, where you're coming in, looking at what's happening, give feedback, you know, several times a day, or at least once a day, if not more. So the once a week model just doesn't work, or twice a week model. And so I think it has to be, in order to bottleneck, in order for it to get fixed, we either have to, you know, force universities to change how the courses are structured and show that it's still, they can still make money from it. Because clearly all the million master's programs that exist are making money, and they're mostly useless, but they're still making money. So if we modified it to kind of be much more useful to the world and to the people who are being trained, I think we have to come up with a business case for it. And that's sort of the missing piece right now.
But the other thing is really about the faculty. I think I definitely started teaching statistics with very limited data experience. Over the years, I acquired enough to feel comfortable doing applied class. So I think I'd like to see more people get hired back from industry to the faculty. And that will be really a boost, right? You look at architecture school, the people who teach practice architect, they are practicing architects or lawyers. And we teach practice of statistics, and most of us, including me when I started, we didn't have practice. And there's a gap there. The only way is actually hiring people back from industry and just reduce the number of papers they have to publish, because a lot of people, and then just say, because they have the practice we need. And also encourage young people to do more practice early on than, you know, keep teaching it without any much until, I mean, some people just don't do it. Yep. And that's a structure change that has to happen.
This might too be relevant to you, Ben and Rebecca. So if you have answers, I'd be curious to hear them. Keith asks, at least to some degree, data science curriculum is driven by what students are seeking and asking for. How do we encourage topics like ethics that might be badly needed, but perhaps not requested by students?
I already put in some answer in the chat box. For me, I was never just serving my students. I mean, I thought being more experienced, we're also guiding them. So I have no problem to say that you have limited experience, I listen to you, but I'm not going to just exactly give you what you ask for. That's teaching, right? Otherwise, we're just serving them. That's not how education works.
And I'll just throw one more question into the mix that we got from Usama. With the hot market demand for data scientists, how can we convince them to do a residency program instead of taking one of the highest paying jobs out there immediately? So this is another question that relates to how much do you have control over the direction that your students go?
Right. I mean, I think on the first question, I don't think we are providing students what they're asking for. I don't think, at least the data science master's programs today don't provide what students ask for. Students are coming in expecting that if they do this master's, they'll get a job. Right? The middle is sort of a black box almost. As we come in, you give me this degree and I'll get a job because employers will hire me because I have a degree in data science. I think in terms of kind of, so I'll give you an example, right? One of students I was in, when I was at the University of Chicago, wrote in the feedback for the class I was teaching, which was machine learning and public policy class. And he said, well, we had this discussion on ethics, like several classes, several lectures. It's not really relevant to me because I'm going to go into the private sector afterwards. And that's exactly why it's relevant to you, because that's what you think. And so I think I agree with Ben, right? Is that we have to sort of, if we're saying that we're producing people who are going to go off and hopefully do useful things in the world, the curriculum we need to kind of equip them with is is done in combination with what the employer is looking for, what society is looking for, what students are looking for, and what academia can provide. So I think there are many, many, many stakeholders other than just pure, just students, because they would just prefer a degree without any training and get a job. So they're not asking for training, they're asking for a job. But we're not providing them a job, we're providing them training, hoping that they then get a good job and they're useful afterwards.
So for Asma's question, I would say that for some of the more ambitious ones, if you stay for the residency, you can make more money in the long run. So you're going to go for short-term money, or you're going to go for long-term money, and you become manager maybe better. So give you all the skills you need to for longer-term fulfillment than just the next couple of years.
Yeah.
Yeah. I mean, the other piece, the little piece is like in a lot of large companies, you can find you're kind of solving very well-defined small problems where you have, 50, let's say you've got 100 people at Google who have a matrix that they're running their logistic regression on to try to get a 0.01% improvement, right? You don't need all the training that all of the things we've talked about to get that job done. But I think for most jobs require that, I think, but then these very well-defined, very narrow, very niche things may not be worth it. So it depends on kind of what kind of, I mean, it kind of comes to life choices, right? What kind of impact you want to have and what are the costs that you can, in some ways, willing to pay for it. And I think we just need enough examples of kind of role models out there who are saying, look, I did this thing this way, and here's my work life, my career, versus if you don't do this, here's what you get. They're both reasonable. It's just what you care about more and what you want to get to.